Great to see you here again. Like I said, we are going to talk about the cryptographic protocols. This is the last video of this paragraph and also of the chapter related to number theory and cryptography. Anyway, the first thing we have to do is to describe what is a cryptographic protocol. Now, we know already that cryptography is about encoding and decoding messages and information, and a protocol is a little bit more, where we have just a way to encode and decode, to encrypt or decrypt. We also have a protocol which describes how to do certain things, how to set up a communication between two parties, for example, or how to identify that the sender is truly the person that he or she claims to be. Now, protocols are used in many other fields. It's not only in cryptography. We also have protocols that doctors have to find or have to follow. In project management, we have kind of protocols. We call them best methods approach to a problem. Also the same way, it's a best way how to do something. Now, the element what we're going to do here is how are we going to set up a system to share those messages. So we have to find out how, or we have to describe what are the different steps, how we create that security, how do we share keys between parties, how do we identify people, and other elements like that. So there are different protocols that we can describe, and here we're going to look at two protocols. The first one is a key exchange protocol. Now, what we want to do is to share private keys. We're dealing with people. We want to be sure that the person we want to communicate with, that they can decrypt our message. Now, we're typically communicating over non-secure media like the internet, and we want to share our private keys with the receiving party. When we want to share those keys, we have to be sure that we only share it with the people who need it, who have access to the information that we are sending. So we have to find out a way how to do this. How can we share that information without endangering the, let's say, the confidentiality of the messages sent? Now, the protocol that is defined to set up that protocol, or the protocol that describes how to share the keys, is what we call the Diffie-Hellman Key Agreement Protocol. It was developed already in 1947 by the British, and it was described by Diffie and Hellman in 1976. The protocol was only made public in 1997, so before that it was used for government applications only. Now, the protocol describes how to share information publicly, even in clear, and that confirmation, that communication makes it possible to create a shared secret key that is hidden from all other parties. Even with sending messages over, information over a clear channel that everybody can read, that everybody can see, they cannot identify the keys that you are creating. So that's in fact very important to be able to do that, because we have to set up a communication with another party, and we don't want to have to share those private keys in different ways, because sharing those private keys in a different way also reduces security. Now, what's going to happen? The Diffie-Hellman Key Agreement Protocol, how does it work? Let's look at two parties. I call them Oliver Twist and Captain Kirk, who want to share secrets of the Federation. And first of all, Oliver and Kirk select a prime number P and a primitive root A of P. So basically they have those two numbers. Those two numbers are known by both of them. Oliver chooses a secret integer, which is k index 1, and sends a to the power k index 1 modulus p to Kirk. Kirk does the same thing. He selects a secret integer k index 2 and sends a to the power k index 2 modulus p to Oliver. Basically what they do is in fact that Oliver calculates a to the power k2 to the power k1 modulus p, and the same thing is done by Kirk. Kirk calculates a k1 to the power k2 modulus p. So basically the elements what they have is that same key that they find, because a to the power k1 to the power k2 is equal to a to the power k2 to the power k1. So basically what we receive here is that both now have the same private key. So basically from point 4, everything is in the green. It means that this is hidden information because only Oliver knows k1 and only Kirk knows k2. So basically doing this, they calculate the same private key. Let's have a look how we can do this with an exercise. Let's look again at those two people. First of all, we select a prime number. It's 101, and a is 99, is a primitive root of 101. We select an integer, secret integer k1, which is 55, and we calculate 99 to the power of 55 modulus 101, which is 32. Then we select a secret integer k2, which is 65, and we send 99 to the power 65 modulus 101, which is equal to 45. So this is all going over the public area. Of course, we don't share the secret integers k1 and k2. Then we calculate ak2 power k1 modulus p, which is equal to 44 to the power 55 modulus 101, which gives us 10. We calculate the other key, which is a to the power k index 1 to the power k index 2 modulus p, is 32 to the power 65 modulus 101, which is also equal to 10. So basically, both now share the same private key, which is equal to 10. And this key protocol, the red areas are in fact public, and the green areas are protected and secret. So using this protocol, we can share those keys under the eyes of everybody, and it's impossible to find out what those keys are. Of course, we have to be careful. Using a prime number 101 is not really a safe solution. We have to select larger prime numbers, but for the computers, that's not so difficult. For us to show how it works, we used a prime number which is rather low. So basically, you cannot use these numbers to have a secret, let's say, communication, but it shows you only how to calculate and how the principle works. Now let's have a look at the other problem that we can consider is a digital signature. Now what you want to do is you want to share information with somebody. For example, I sent you information that you have to send me some, or that you have to do something, or that you have to meet at a specific place. And I want to be sure that that information comes from the person that I think it comes from. I want to be sure that the sender of the message is really the person I expect or that I know. Now, what can I do here? So we have to be sure that the sender is the person who that person claims to be. So I have to find a way how to do that. And how do we do that in this way? Just imagine Captain Kirk wants to send a message to the crew. He has a public key N and E and encrypts a plain text message M plain with the encryption function E with NE, M plane, is M plane to the power E modulus N, and decrypts a ciphertext message, MC, using the decryption function. So we have DND of MC is equal to MC to the power T of modulus N. So basically, the encrypted message is then decrypted by using the public encryption key, which is available for everyone. Now, what we do now is to look at the exchange. How do we exchange? Let us say you want to message freedom to different people. You have selected N is 2911, which is 41 times 71, and E is 11. Based on this, we find a decryption key, which is the inverse of E modulo P minus 1 Q minus 1. Or we can say that 11 times D is congruent 1 modulus 2800. And we can find that this complies with D equals 1091. And we can find that using the property that 2800 divides 11 times D minus 1. Or 11 times 2291 is equal to 1 plus K times 200. Now, what we have to find now is that we have to go to the next element. So we have to write freedom in numbers. We group them per 4. Since we have the 2525 smaller than 2911, and 2525 is larger than 2911. And we find the numbers 0517, 0404, 0314, 1223, and we find the encrypted values. We're using the program, which is 517, 20 to the power 2299, modulus 2911, and so on. So we find those different elements and we calculate the different results. So basically we find here the encrypted values 0968, 1397, and so on. Based what we're going to do now is we receive the coded message 0968 1284 1379 2069. So we want to know if this message came from the right person or not. When we apply the encoding key on each block, we should be able to receive the original message. And this leads to the following equations. 968 to the power modulus 2911 is 0517. We do the same for all those blocks and we find 0517, 0404, 0314, and 1223. And basically we find a result which is the original string, or it is freedom with an X and the X has no value. So basically the message that was sent was freedom. So basically what we did here, we looked into the different protocols about the ways how to share messages, how to share keys over a public network, and how to identify the sender using those different cryptographic protocols. In the next chapter, this was the last video of the 4th chapter, we're going to start with a new chapter after these videos, of course, and we will be talking about induction and recursion. You're doing a great job. You finished another chapter. There's still a lot of work to continue, but you're doing a great job, and I'm looking forward to seeing you in the next video. Thank you, and bye-bye.